For 40 years, one material separated the aircraft that could from the aircraft that couldn't. Carbon fiber, stronger than steel at 1/5 the weight, became the defining substance of modern aerospace. The Boeing 787 Dreamliner is 50% carbon fiber by structural weight. The F-35 is 35%. Every serious missile casing, every next-generation airframe, every lightweight defense platform built in the last 2 decades carries that same dependency. And for those same 4 decades, the supply chain behind that material ran through a small number of Japanese and American producers. Toray Industries alone supplies the majority of the carbon fiber in every 787 Boeing has ever delivered. That arrangement was not a coincidence. It was the product of decades of precision manufacturing expertise, qualification barriers, and IP moats that made meaningful competition appear structurally impossible. In 2024, China's domestic carbon fiber output crossed a threshold that rewrites that assumption entirely. The story of carbon fiber's dominance in aerospace does not begin with a breakthrough. It begins with a relationship. In 1974, Boeing and Toray Industries of Japan signed the first supply agreement that would eventually make a single Japanese chemical company the material backbone of the most commercially successful aircraft program in history. That relationship was not the product of chance. Toray had spent the previous decade developing a manufacturing process for polyacrylonitrile-based carbon fiber that produced consistency at a level no competitor had matched. Boeing recognized what that consistency meant for structural engineering. The agreement was renewed, expanded, and deepened across 5 decades until it became something closer to a dependency than a partnership. The numbers that dependency produced are worth stating plainly. The Boeing 787. Dreamliner, which entered commercial service in 2011, is 50% carbon fiber by structural weight. No commercial aircraft. Before it had crossed 20%, the decision to build at that ratio was not an aesthetic one. Carbon fiber allowed Boeing to replace aluminium in primary structural members, fuselage barrels, wing boxes, tail assemblies, and achieve a weight saving that translated directly into the 787's signature 20% fuel efficiency advantage over the 767 it replaced. That figure is the commercial case for the entire program. Without the carbon fiber, there is no case. The military dependency runs on a parallel track. The F-35 Joint Strike Fighter carries carbon fiber composite in approximately 35% of its structural weight, concentrated in the airframe sections where radar cross-section and load-bearing requirements intersect. The B-2 Spirit bomber is higher still. Missile casings for programs including the JASSM and the SM-6 use carbon fiber for the same reason aerospace does. The strength-to-weight ratio at the temperatures and pressures of sustained flight has no equivalent in metals. Named programs, named materials, named producers. The supply chain ran from Toray's facilities in Japan through a qualification process managed by Boeing, Lockheed Martin, and the U.S. Department of Defense, and it ran that way for 4 decades without serious interruption. It is worth pausing on what carbon fiber actually is before the industrial argument proceeds. A single toe, the basic unit of production, contains between 1,000 and 50,000 individual filaments, each roughly 7 microns in diameter. Human hair runs between 50 and 70 microns. Each filament is almost entirely carbon, arranged in a crystalline structure that gives the material its tensile strength. Holding a spool of carbon fiber tow, you are holding something that feels closer to thread than to a structural material. The properties feel almost fictional until the engineering data confirms them. The assumption encoded in every aerospace supply chain built on this material was straightforward. Japan and the United States controlled aerospace-grade carbon fiber production. The qualification barriers made entry by any new producer a decade-long process at minimum, and the IP moat around precursor chemistry and carbonization, process control, made replication without that foundation close to impossible. That assumption was not naive. It was accurate for a very long time. Carbon fiber is graded by tensile strength. The industry shorthand runs T300, T700, T800, T1000, each step representing a meaningful increase in the force required to break a single filament under tension. T300 is the baseline industrial grade, used in sporting goods, automotive panels, wind turbine blades. T700 is the workhorse of mid-tier structural applications. T800 is the threshold. Above T800, you're in aerospace qualification territory, the grade that Boeing, Airbus, Lockheed Martin, and their defense counterparts specify for primary structural members. T1000 and above is where the most demanding military applications sit. As of 2015, China produced no certified T800 grade carbon fiber. That statement requires unpacking. Chinese producers, principally Zhongfu Shenying and Sinofibers, had been manufacturing T300 and T700 fiber for domestic consumption since the mid-2000s. Wind turbine blades in Xinjiang and Gansu carried Chinese carbon fiber. Consumer sporting goods carried it. Domestic civil infrastructure projects used it for retrofit reinforcement. None of that production touched aerospace specification. The gap was not a quality gap in the ordinary sense. It was a precision manufacturing gap. The difference between producing fiber that is strong enough on average and producing fiber whose consistency across an entire production run is tight enough that a structural engineer can sign off on it for a primary airframe member. The certification barrier reinforced the technical one. Boeing's qualification process for a new carbon fiber supplier requires a minimum of 5 years of documented production data, lot-to-lot consistency testing, and independent structural validation. Airbus runs a parallel process of comparable duration. A Chinese producer that achieved T800 grade fiber consistency in 2015 would not appear in a Boeing qualified supply chain before 2022 at the earliest, assuming a flawless qualification campaign. No such campaign was running in 2015. The Comac C919, China's first domestically developed narrow-body commercial aircraft, entered service in 2023 with a carbon fiber composite content of approximately 12% by structural weight. The 787, its long-term competitive target, carries 50%. That gap was not an oversight. It was a deliberate engineering decision made during the C919's design phase to reduce the program's exposure to a domestic supply chain that did not yet exist at the required specification. The C919 was designed around what China could make. The 787 was designed around what Toray could make. What changed between 2015 and 2023 has a specific institutional address. Zhongfu Shenying, based in Lianyungang, Jiangsu Province, began reporting T800 grade output figures in 2021. By 2023, its declared annual production capacity for T800 equivalent fiber had reached 12,000 tons. The trajectory implied by those numbers, not the numbers themselves, is where the story turns. Making aerospace-grade carbon fiber is one problem. Using it is another. The distinction matters more than it is usually given credit for, because the history of Western carbon fiber dominance is not only a story about who could produce the material, it is a story about who developed the industrial processes to turn raw fiber into certified structural components at production scale. That second capability took as long to build as the first, and it is the one that determines whether a carbon fiber supply chain can actually serve an aerospace program. The central process is automated fiber placement. AFP machines lay carbon fiber towels onto a mold surface at precisely controlled angles under precisely controlled tension at speeds that make hand layup economically unviable at program scale. A single degree of angular error in a primary structural member is not an imperfection, it is a failure mode. The machines that performed this operation to aerospace tolerance were, until recently, manufactured by two Western companies. Electro-Impact, based in Mouchelteo, Washington, and Coriolis Composites, based in Caen, France. Between them, they supplied the AFP equipment underpinning the 787 line at Everett, the A350 line at Toulouse, and the majority of Western defense composite programs. That duopoly was not incidental. AFP machine development requires the same kind of precision engineering and process knowledge accumulation that carbon fiber production itself requires. It compounded the barrier. Following the expansion of the U.S. Entity List in 2019 and subsequent export control tightening through 2022, direct transfer of AFP technology to Chinese aerospace manufacturers became legally constrained. The policy was designed to slow Chinese composite manufacturing capability, By the time it was implemented, Avic Composite Corporation, the composites arm of Aviation Industry Corporation of China, had been developing domestic AFP capability since at least 2016. The export controls arrived after the foundational work was already underway. The process shift that accompanied China's AFP development was the move from pre-preg to dry fiber resin transfer molding. Pre-preg, carbon fiber pre-impregnated with resin before layup, generates material waste of approximately 40% during cutting and forming. Dry fiber RTM, which injects resin into a preformed dry fiber structure under pressure, reduces that waste to under 15%. The arithmetic is not subtle, not faster production, cheaper production. A finished structural panel coming out of an RTM mold looks different from one built by hand layup. The surface is uniform, the resin distribution consistent, the void content measurable and repeatable. It looks, in short, like something made by an industrial process rather than a skilled trade. That distinction is what program-scale manufacturing requires. In 2018, aerospace-grade T800 carbon fiber from Toray traded at between $80 and $120 per kilogram, depending on contract volume and specification. That price reflected 4 decades of accumulated process knowledge, the cost of maintaining carbonization furnaces to aerospace tolerance, and the margin structure of a supplier with no credible competition at that grade. It was expensive, and the programs that depended on it had no alternative. The cost was treated as a fixed condition of doing business in advanced aerospace. By 2024, Zhongfu Shenying and Sino Fibers were supplying T800 equivalent fiber to domestic Chinese aerospace programs at contract prices in the range of $35 to $45 per kilogram. The differential is not a rounding error. It is a structural cost gap driven by 3 compounding factors: domestic polyacrylana trial, precursor supply at state-supported pricing, energy costs at Chinese industrial rates, and production scale that has now crossed the threshold where unit economics diverge permanently from smaller volume Western production runs. That last factor requires a number. China's total carbon fiber production capacity crossed 100,000 tons per year in 2023, according to figures published by the Japan Carbon Fiber Manufacturers Association and corroborated by independent industry analysis. Japan's total production capacity across Toray, Teijin, and Mitsubishi Chemical combined runs at approximately 50,000 tons per year. The United States, through Hexcel and Solvay's domestic operations, adds roughly 20,000 tons. China now produces more carbon fiber by volume than Japan and the United States combined. The volume advantage feeds back into cost. Longer production runs, higher furnace utilization, lower per-unit energy allocation. Boeing's exposure to this arithmetic is specific and structural. The 787 program consumes approximately 23 tons of carbon fiber per aircraft. At the price differential between Toray's supply and Chinese domestic production, the material cost gap per aircraft now exceeds $500,000. Across a 787 production rate of 5 aircraft per month, that gap compounds to over $30 million per year on a single program, on a single material. Boeing is not paying Chinese prices. Boeing is locked into Toray supply agreements that stretch across the remaining life of the 787 program, because the FAA qualification process for a new carbon fiber supplier would require a minimum of 7 to 10 years to complete even under optimal conditions. The lock-in is the operative word. Not a price disadvantage. A structural cost gap from which there is no near-term exit in a market where COMAC is preparing to compete for the same narrow-body and wide-body orders using a domestic supply chain that does not carry that gap. Boeing's 2023 supplier dependency disclosures, filed as part of its annual risk reporting, identify Toray as a sole source supplier for specific carbon fiber grades used in the 787 program. The language is careful. The implication is not. A sole source designation for a primary structural material in a program with a 400 aircraft backlog is not a supply chain configuration. It is a vulnerability with a name attached to it. That is the official picture. Here is what the supply chain data shows. The FAA's qualification process for composite materials in primary aircraft structures requires a documented production history, lot traceability, and independent structural validation that cannot be compressed below 7 years under current regulatory frameworks, regardless of how technically capable the new supplier is. This is not bureaucratic obstruction. It is the engineering logic of certifying materials whose failure mode in primary structure is catastrophic. The consequence is that Boeing's exposure to its Toray dependency cannot be resolved by procurement decision. It can only be resolved by a qualification campaign that takes a decade to complete and has not yet been initiated for any alternative supplier at T800 grade. The defense exposure operates on a parallel track with an additional layer of complexity. The F-35 program's primary carbon fiber supply runs through Toray's manufacturing facility in Decatur, Alabama, a domestic U.S. production site which satisfies the Buy American requirements of defense procurement. What the facility designation does not fully resolve is the precursor dependency. The polyacrylonitrile precursor used in Decatur is partially sourced from upstream supply chains that run through Japanese chemical production. Supply chain sovereignty is not determined by where the final manufacturing step occurs. It is determined by who controls every input to that step. What a 6-month disruption to carbon fiber supply would mean for the 787 program at Everett is not speculative. Boeing's production line operates on a just-in-time material flow calibrated to the current delivery schedule. The 787 backlog as of mid-2024 runs to approximately 450 aircraft. At 5 aircraft per month, a 6-month material disruption does not produce a 6-month delay. It produces a cascade: rescheduled deliveries, penalty clauses, customer financing complications, and a production restart that takes longer than the disruption itself. The Everett line is not designed to absorb that kind of interruption. Western aerospace is one sustained geopolitical disruption away from a material constraint it has no short-term answer to. That is not a projection. It is the arithmetic of the supply chain as it currently exists, stated without the qualifications that official risk disclosures are required to include. The COMAC C919s. 12% carbon fiber content by structural weight is the number most frequently cited when Western aerospace analysts argue that China's composite capability remains immature. The comparison to the 787's 50% is intended to be reassuring. It is the wrong comparison to make. The relevant number is not where the C919 sits today. It is where COMAC's next-generation wide-body program, the C929, developed in partnership with Russia's United Aircraft Corporation, is targeted. COMAC's published program documentation sets a composite content target for the C929 above 40% by structural weight. That target is achievable with the domestic supply chain China has built. The 787's 50% was achievable because Toray existed. The C929's 40+% will be achievable because Zhongfu Shenying, Sino Fibers, and the CFRP Valley Industrial Cluster in Xining, Qinghai Province exist. The CFRP Valley deserves a specific mention. Established under state direction in 2019 and expanded through 2023, it is a carbon fiber industrial zone occupying over 200 square kilometers of the Xining Economic Development Area. Its anchor tenants include fiber production, precursor chemical manufacturing, AFP equipment development, and composite structure fabrication, the full vertical stack, co-located and state-subsidized. The zone's declared output target for 2025 is 50,000 tons of carbon fiber annually from the Xining cluster alone. The military application of the same supply chain requires no inference. The J-20 stealth fighter carries an estimated 20 to 25% composite fraction by structural weight, with carbon fiber concentrated in the airframe sections governing radar cross-section. The PL-15 Extended Range Air-to-Air Missile uses a carbon fiber casing qualified to the thermal and structural demands of sustained supersonic flight. These are not prototype qualifications. They are production program qualifications, which means the consistency and lot-to-lot repeatability of Chinese T800 grade fiber has been validated by the most demanding quality regime that exists, military airworthiness certification. The same fiber, the same AFP machines, different end products. The dual-use nature of the capability China has built is not incidental to its strategic value. It is the point. One worker at the Yining CFRP Valley described the facility's pace of expansion in 2023 as unlike anything in the prior decade of Chinese composites manufacturing. New carbonization lines commissioned every quarter, equipment that would have taken 3 years to source externally now built domestically in 18 months. That pace is an industrial policy decision made visible at the factory floor level. What Boeing built over 40 years with Toray, China has rebuilt domestically in less than a decade, and it did so while Boeing was still celebrating what it had built. Block, Section 6, Chakach word count, approx. 428 words. The United States Department of Defense's 2023 report on critical material dependencies identified carbon fiber as a Category 1 supply chain vulnerability, the highest designation in the DoD's risk taxonomy. The report noted concentrated foreign production, limited domestic surge capacity, and qualification timelines incompatible with rapid industrial response. It recommended investment in domestic precursor production, expansion of Toray's Decatur facility, and accelerated qualification programs for alternative suppliers. It was a precise and accurate diagnosis. What followed that diagnosis is the section of the story that requires the most careful reading. Toray's Decatur, Alabama facility, the primary domestic U.S. carbon fiber production site for defense-related programs, operates at an annual capacity of approximately 15,000 tons. The 787 program alone consumes in excess of 1,400 tons per year. F-35 production adds several hundred tons more. The remaining capacity services other aerospace and defense customers. The arithmetic of domestic supply versus program demand leaves almost no margin for surge, diversification, or the kind of stockpiling that Category 1 vulnerability designations are supposed to prompt. The DoD report recommended expanding Decatur's capacity. No funded expansion program, at the scale the report implied was necessary, has been publicly announced. The European picture runs parallel. Hexcel, headquartered in Stamford, Connecticut, with primary manufacturing in the United States and the United Kingdom, and Solvay, headquartered in Brussels with carbon fiber operations in Wrexham, Wales, represent the core of Western non-Japanese carbon fiber production outside Toray. Their combined output at T800 grade specification is estimated at under 30,000 tons annually, against a Chinese production base that has crossed 100,000 tons. The capacity gap is not a planning problem. It is a capital investment problem of a scale that no private company has yet committed to solving without government underwriting. The export control response warrants a direct assessment. The restrictions placed on AFP equipment, transfers to China through the Entity List, and EAR amendments between 2019 and 2023 were designed to slow the development of Chinese composite manufacturing capability. Avic Composite had been developing domestic AFP equipment since at least 2016. The export controls arrived after the foundational development work was complete. Restricting the transfer of AFP machines to a country that has already built its own AFP machines is a policy calibrated to a threat that no longer exists in the form it was designed to address. Building a competitive T800 carbon fiber facility in the United States from groundbreak to aerospace qualification takes between 8 and 12 years and requires capital investment in excess of $2 billion. No such program is currently funded at that scale in either the United States or the European Union. China now produces more aerospace-grade carbon fiber by volume than Japan and the United States combined. It produces it at roughly 40% of the cost. The supply chain behind the F-35 and the 787, two programs that define the current generation of Western aerospace, runs through a qualification architecture that cannot be redirected in under a decade. These are not projections. They are the current state of the industrial landscape measured in tons, dollars per kilogram, and certification timelines. This is not a technology race that the West is losing. That framing is too comfortable because it implies a competition still in progress with an outcome still in doubt. What happened in carbon fiber is closer to a structural shift that completed itself while the policy response was still being drafted. The material that makes the 787 commercially viable and the F-35 structurally possible is no longer exclusively in Western hands. The The qualification lock-in that keeps Boeing and Lockheed inside their existing supply chains buys time. Time is not a strategy. What the Western response will look like over the next decade is genuinely uncertain. The DoD report exists. The vulnerability is named. The capital requirement for a credible domestic response. Multiple new T-800 grade facilities, precursor supply chain investment, an accelerated qualification program. Runs to figures that require legislative commitment, not departmental recommendation. Whether that commitment arrives before the qualification lock-in on current programs expires is the operative question. There is no confident answer available at this point in the timeline. Whatever the geopolitical context in which China's carbon fiber program was built, what was built is an industrial achievement without precedent in the history of advanced materials manufacturing. A supply chain that took Japan 40 years to develop, with the full benefit of early mover advantage, process knowledge accumulation, and deep customer relationships, was replicated domestically in under a decade, at lower cost, at higher volume, with military qualification. The grudging acknowledgement that this represents is not a political position. It is an engineering assessment. The question the timeline forces into the open is a genuine one, without a predetermined answer. Do you think Western aerospace can rebuild this supply chain before the qualification lock-in on current programs becomes a strategic liability? Or has that window already closed? If this changed how you think about the materials behind the aircraft and weapon systems the West depends on, give it a like and subscribe for more analysis of the industrial and technological shifts quietly reshaping the global balance. Turn on notifications so you never miss one. And leave your answer in the comments. The conversation there is worth reading.